morning. My name is Chafika Phiri, and I'm a PhD student. And my poster is about mapping African Baobabs used with Worldview 3, Sentinel-2, and PlanetScope images. So the motivation behind this work is right now, Baobabs trees are facing a lot of pressures because of rapidly growing land use changes, climate changes, as well as unsustainable utilization on the continent of Africa. And in this poster, which is part of my PhD topic, whose aim is to investigate the distribution of baobab trees and their utilization across the continent of Africa, we'll be testing we'll be testing remote sensing data and unit modeling, map baobab trees, as well as evaluate the spatial and temporal baobab mortality due to elephant damage in two distinct areas in northern part of South Africa. And I'll be using unit model. So we chose this model because of its capability to work with a small data set. And right now, at the initial stage of developing the model and doing data processing. So we don't have initial results from the model yet. So I'm looking forward to for you to visit my poster to share what I'm doing and as well as to learn from you. Thank you.
Hi everyone, I'm Jess Thomas. I'm in the final year of my PhD here at the University of Exeter, and I do have a poster talking about my recent work on predicting soil carbon from remotely sensed canopy structure metrics in the Amazon. The overall objective, the point of this study, first and foremost, is development of methods. So we're hoping to improve on current methods of predicting soil carbon concentrations in the Amazon by including remotely sensed canopy structure metrics. But within that, I'd also like to test if the predictive accuracy changes with different sources of canopy structure metrics to identify the best methods and the most appropriate uses of doing this work. And then finally, because I'm kind of using a slightly unconventional use of machine learning, I'm also working to verify our machine learning results by using a more traditional statistical approach of generalized linear modeling to investigate the underlying mechanistic relationships. But why should you guys come to my poster? Like I said, it's a somewhat unconventional use of machine learning, and I would really like to gather people's feedback on that. And I know everybody loves to get their opinion. I'm also at a stage of editing this work, hopefully for publication soon, and so I'd really love to check all my communication and make sure that that's approaching the right audience. And finally, it's a fun game. You can test your own theory. You can take an educated guess at which source of canopy structure data you think produces the most accurate predictions of soil carbon concentrations. Your options are spaceborne LiDAR, airborne LiDAR, or in-field photography, and you'll find out the answer if you come to the poster.
I'm Geoffrey, I'm from IBM, and this is our poster, a sensor-free foundation model for marine applications. So this work follows closely the work that Andy's going to talk about later on today, but a lot of applications of foundation models have been over land, and we thought we could try it over the ocean, probably because I think the ocean is probably slightly more interesting than land, but that's out there. And this was done in collaboration with Exeter and PlanetScope. And the reason why we did it really is because foundation models are very good with low amounts of labeled data. And over the ocean, you generally have a lot of low amounts of high quality labeled data, mainly from shipborne observations and ports. So that's what we've done. we created a foundation model from Sentinel-3, mostly the ocean land current instrument, and we've also included the sea surface temperature. And then we tried it on 2 downstream tasks. We tried primary production quantification and half of hour balloon protection. And if you come to the poster, you'll get to see some of the results. It's a big one because I didn't read the thing properly, so mine's a big A0 poster. A1. It's easy to spot. So thank you.
Hi everyone. So I'm Charlie Gertwood. I've been working with Steve Palmer on this project. He is probably the best person to talk about it, but he couldn't be here just now. So we've been basically trying to see whether you can improve the monitoring of coastal erosion by interpolating temporally between snapshot LiDAR surveys that are taken every couple of years or so, using the information that's available from satellite imagery. So satellite imagery is collected something like every 8 days. I think the Landsat would go over a certain area. So that gives you high temporal resolution, but obviously the satellite image itself isn't recording exactly the state of the coast. It's quite low resolution data, and it doesn't measure, say, elevation directly, whereas the LiDAR survey is very high spatial resolution and gives you kind of pinpoint accuracy of the lie of the coast, so exactly what the cliff looks like at any given time. But the LiDAR survey is expensive to collect. It's only collected every couple of years or so, depending on which part of the coast you're at, and this is in the UK. Other parts of the world maybe never get a LiDAR survey. So ideally, you'd probably have a LiDAR survey every day, and then you could just monitor all the changes that happen to the coast. And the reason we want to be able to do that is so that then you can attribute the coastal erosion to various climatic condition factors. So if there's a storm, it would be great to be able to link that with exactly how much coastal erosion it caused. And heavy rainfall, again, exactly how much of a cliff collapse does that cause? So if we had this kind of perfect knowledge of the coastal state, we'd be able to make quite detailed models of how climatic conditions affect coastal erosion. But we don't have that, but we do have satellite imagery, and we want to be able to kind of learn a mapping between the two. So that's what we've been trying to do here. I think I've probably spoken for too long already. This is an animation, though, just to show you. Yeah, in the bottom right here, this is what the satellite imagery actually looks like when you consider that most of the time it's just a cloud, because we are in England after all. So there is initially quite a big issue in basically infilling the clouds, and then once you've got something like a cloud-free satellite image, then you can map from that to what the coastal elevation looks like. Anyway, I think I've explained that in a very rambling way. If you want to find out more, then speak to Steve, who will be around later, or you can ask me about it too. And also Christina Coker and Stefan Siegert, who might also be around at some point. We're all University of Exeter. Cool, thanks.
Good morning. My name is Tom. I'm a PhD student at King's College London, supervised by Professor Matt Musa. I'm talking about how our work is in AI and Earth observation from landscape fires. Some background about mass burning is a major source of atmospheric pollutants and greenhouse gases. And we're using direct top-down approach using satellite retrieve bioradiative energy and the concentration profiles for more direct emission estimates. So the value of emission coefficients are derived from multiple coincident environment and plume observation at the same fires. So currently, this work mainly rely on manual identification of these matchup plumes and active fires, which is highly inefficient for large-scale study. So we proposed an automated approaches that using united deep learning model. So we combined two main satellite inputs, Sentinel-5P column carbon monoxide and verse active fires. to predict isolated plumes. So the initial training shows that the results is the model is able to learn the plume features, but however some plumes are interconnected, making the individual fire analysis difficult. So we also proposed post-processing to prepare data sets that only contain isolated plumes, and retrain those with a fine-tuned model. So the results show that we're getting all the isolated plumes, making the results significantly improved. So this work is now able to making a global analysis of emission coefficient.